Hello, and welcome back to the last part of properties of intermolecular forces, specifically looking at molecular compounds, so things that are covalently bound. So, this one, we're going to be just looking at some demonstrations of how hydrogen bonding can affect some of the different properties of materials. So, how does this all come about? Well, if you kind of think of it in terms of particulate theory, which was all about how different particles interact with one another, we've used this description on all these videos for a really long time of how we can see that we have these particles, they're constantly moving. Now, one thing about them is when they interact with one another, this takes a lot of energy in order to separate them from one another. So they like to be interacting with each other. So when we are looking at something like this is known as a potential energy surface, which essentially the lower you are in this little well here, the lower the energy is, the more relaxed the molecules are. So one thing you can see is, okay, when they're two little orbs here, they're really close together. This is like at the very bottom. This is as relaxed as they can be. They're really happy there. Now, the farther you pull them apart, it's going to take energy to pull them apart. So the farther you get away from this line here, the farther you come away from each other, the more they're going to get pulled apart. And it takes energy to do that. So what this means is the stronger the intermolecular force is, the deeper this well is, meaning it's going to take a ton of energy to separate, say, hydrogen bonding versus dispersion. Dispersion's like you can blow on it, it'll fall apart. So that's what we're going to look at today. Is the strongest the intermolecular force is, the more force. So one thing to kind of think about is the more, how can this have an effect on big bulk properties of what you visually can see, is what we mean by bulk. So when you have like a cup of water or something that's sitting around your house, you can observe those things. So things with stronger intermolecular forces usually have a higher boiling point. The other thing that gets affected is if they match, we have the solubility or the miscibility of how they mix together can get affected too. So matching forces, like dissolves like, is a factor. So let's take a look at some of these things. So we learned about melting point and boiling point. What else can we have? Well, the first one is surface tension. So what that is all about is being, if you have, let's say, water molecules that are on a in it within, you take your little atom microscope and you look at that level, all of the water will interact with each other, making a hydrogen bond network. And we've looked at similar things to like this in the past. One would be if I were to, let's say, play this video like this one here, and we were to look at it again, well, on the left-hand side, you can see that there is a network of all these molecules. They are hydrogen bonding to each other. On the right-hand side is all dispersion forces all interacting with one another. Now, the more this thing heats up means it has more energy. All the little particles are kind of dancing around more and more and more. They're moving at a really high rate. As a result, it's going to start moving and breaking and changing. It's going to affect their properties. So something that has a really strong intermolecular force can have a really high surface tension, meaning you can kind of walk on water in a sense. Versus, can you really walk on air? It's not necessarily possible right without an airplane. It takes a lot of engineering marvel to be able to do that. So the stronger that framework is, the more we're going to actually see there. Let's take a look at what this looks like in another demonstration. When it comes to surface tension, when we're trying to think of this, the ultimate way is thinking of like bugs and frogs on water, right? They can walk on the water because of the webbing of their feet. Well, another way to see this is on the International Space Station, they're always doing water demonstrations to illustrate some of the different properties here. So water can do hydrogen bonding, meaning that it's being held together with this intermolecular framework. So what we're actually going to be seeing is essentially Chris Johnson, who's one of the astronauts on the space station, is going to collect water with a paper towel. It's going to kind of demonstrate how they can actually like wash their face and things like that. But you can see like water, he can actually like shoot it out of the water bottle, and now the towel has absorbed it all. Now, what you're going to see here is when he kind of start to wring it out, is you'll see the layer of hydrogen bonded water molecules all around this thing. So it's showing how surface tension is holding together. So look at the little water layer that is there. And this is something you can't do easily on Earth, but water can easily hydrogen bond and hold itself together, right? You can't see this with other molecules at any normal given temperature. So water's able to hold itself together like this. And you can see how it spreads all over his hands. It's on the paper towel. And it's because of the effects of gravity that make this possible. But the surface tension of hydrogen bonding is what really allows this to be possible, which is really like a really cool effect to see. So hydrogen bonding is a fantastic thing to be able to observe, where we can see it firsthand via like from others from around the planet or from space, right? To show how we can see this. The other example is by imagining how, let's say, insects can actually interact with water, right? They can essentially walk on water. We can see that effect. It's really cool to see how that is. Now, you don't need to know the mathematics behind this for my course, but if you're curious for physics, then we can really see that. What other forces are there? Well, there's also viscosity, which is the other one. So how thick or goopy a substance is. So when it came to surface tension, you can easily see that. An easy way to do it is if you ever filled a glass of water and you essentially filled it to the point where you thought it was going to overfill, but it didn't. So you'll see that bubbled layer on the top of the water. That is one way to imagine it. Viscosity is the resistance for liquids to flow, meaning the stronger the forces, the harder it is for that to flow. So one way to kind of think of this is the bigger the molecule, the tougher it is. So here I have a bunch of viscosities for different levels of carbon. And we can see that the numbers on the far right-hand side are increasing, going from one molecule to the other. So what exactly does this look like in terms of bigger molecules, higher dispersion, when we can see this change? Okay, so in this video, what we're going to be looking at is I found a video on YouTube that has viscosity races, essentially using different ingredients found in food. So here what we have is from left to right is maple syrup, ketchup, mustard, and honey, so which are going to be used here. And pretty much something you could do at home if you wanted to do it with really young kids, but essentially the viscosity is how fast is it going to flow. So syrup, as you know, is a really sticky substance. It's actually usually really slow, especially when compared to water, right? But if you think of these other different ingredients, which are a lot heavier of a molecular composition and have bigger molecules, they flow very, very, very slowly when they're on a plate, right? So the stronger the intermolecular force is, the higher the dispersion is, the slower it's going to move, the thicker it is for the substance to actually move from one to the other. So you can kind of see, like looking at these, going from syrup to honey to ketchup and mustard barely moving at all, the higher the viscosity, the slower it's going to be. So if you were trying to figure out which of the molecules here would have the highest viscosity, what could you exactly try to compare? Well, looking at all of them, and the same idea was with surface tension, was that you want to be able to compare what forces they have. Now, with all these, all of them have dispersion. They see CH4, C2H6, C3H8. They're all nonpolar. Same thing with CF4, CCl4. They're all mainly tetrahedral. They all have nonpolar bonds. They are things that, and they all cancel out. They're dipoles as well. So what can you exactly look at? Well, you're going to try to see which one has the most electrons or the highest molar mass is another way of looking at it too. So out of all these, right, you can tell that going from A through C, C would be bigger than B and A. But what about with these other two compounds down here? They're a little different. Well, CCl4 is bigger than CF4, so you're pretty much comparing C and E. Well, looking at them, each chlorine has 17 electrons. That's almost more than a lot of this compound here, right? 2 chlorines would be more than just almost one of these. So E is going to have the most electrons, which is the highest polarizability out of all of them, right? Linking together, dispersion, all these forces. Now, the other different properties we're going to look at too is vapor pressure. So what do we exactly look at? Well, this is how easy it is for a chemical to become a gas without boiling, right? So chemicals vaporize all the time. One way to think about this is if you go outside in the early morning, you'll see that there's dew on all the grass and leaves and in your car in the early morning. But does it sit there all day? Over time, you see that that evaporates. So when it gets really cold at night, it condenses, and then over time it evaporates because it gets enough heat or energy. The water isn't boiling off the grass; it's vaporizing. So it does have enough energy for it to push against the atmosphere and to leave and become a vapor. So it's all these little gas molecules trying to escape. So this is something that constantly is happening, right? You have the liquids here. You always have a little bit of gas above the surface level, which is also possible. You've seen it in my demonstration with water molecules. There actually were little gas molecules floating above before. So it's the push, essentially. Are the liquids trying to escape? They are being held back by how strong those intermolecular forces are, but some of them are able to break free when they're trying to get out of there. So when we're looking at this, something that's volatile means it can easily evaporate. Non-volatile does not. So what that means is the stronger the intermolecular force is, the lower the vapor pressure, meaning it's going to be non-volatile. So something that doesn't break. So what is volatile? Well, think of when you go fill your car up. One thing that they tell you not to do is don't smoke near the gas tanks, why is that? Because gasoline is volatile, meaning that the gas that you can smell is in the air. So if you kind of light a cigarette or something, it's going to potentially make the gas pump explode. So it's one of those things that you gotta kind of think about. So the stronger they are, if it goes from, let's say, a liquid to a gas, it could still be holding in place. Whereas if you heat it up or give it enough energy, right, through heat, then it could potentially break apart without even reaching the boiling point. So this is volatile on the right and non-volatile on the left. So this is something that's like a dynamic process. So this is one of the reasons why we keep volatile liquids in sealed containers. Think of your gas tank. You got to close the cap every time you do it. If you didn't, then all your gas would be evaporated out of your car by the end of the day if you were not doing that because of this state of dynamic equilibrium. The liquid that's at the bottom here is constantly turning into a gas, and it's going to kind of bounce all around its container and then kind of make its way back into the liquid and continue to cycle through. It's going from out, then back in, and it constantly moves from one area to the other. So this is what we refer to as dynamic equilibrium. So to kind of like wrap it up, what we're trying to say here with dynamic equilibrium is that evaporation, which is all about where you have something that has a low temperature molecule. So here's all the molecules. They're all mainly lower temperature. They don't have a lot of energy. And they're below what we would consider is the escape point. So kind of like where it's boiling, where it has enough energy. So one of the things that makes this easier, well, what can accelerate it? Well, is it all clumped together or is it spread out over a big surface? So one way to think about this is if you have like a glass of water, and let's say you spill the water all over the counter, and you put them both next to each other, which one will evaporate first? Typically, it's the liquid that's spread over your whole counter because it's interacting with more things that can excite it to a higher temperature. So if these things get hotter, then what's going to happen is more molecules are going to be able to escape that gas phase and go into the gases. So it's not all of them will become gases, but over time you'll see things will evaporate. This is what's happening outside on your car, right? In the early morning, all of that dew that's on your car and on the grass, it's in that lower temperature, but as the day gets hotter and hotter and hotter, more of it has enough energy that's been absorbed from the atmosphere, from the sun, to be able to heat up and to become a gas. Not boiling, but it's enough to evaporate. Now, to compare the two, right, boiling means that essentially the liquid vapor pressure matches air pressure because it got so much energy where it's now able to actually break through and join the gas phase. Okay, so that's all I have for intermolecular forces for this set of lectures. I hope that these videos helped you try to understand a little bit more. Good luck trying to do all your homework assignments out there. And thank you so much for listening. And please, if you have not yet, hit that like, subscribe button. I hope to see you all in the future. Bye now.